Oh, wait. Now we are ready. All right.
Perfect. Great. So where are we at? Just as an intro, if you hop to the next slide, kind of Henry Ford, the automotive industry, and Thomas Edison meet. If you are going to the next slide, please. And that's also, if you click again, what the story of Mobility House is. And I would like to give you a very brief intro about us, why V2G is necessary, and speed up there because some things have said already. How do we see the roadmap as Mobility House, and give you some examples and what would be the key requirements from our perspective. Next, please. So I think it's absolutely clear, and Vincent made that clear already before, that the automotive industry and the power industry is moving together. And now Xaver said that also before, we will have 10 million cars in Germany, most probably 30 million cars in Europe by 2020-30. This seems long in general. For the energy industry, this is not long at all. In 10 years within the energy industry, you do not move a lot. So there will be a huge pressure pretty soon on the whole energy system, and I'm looking forward when Axel Kiesling is telling us about that in the next presentation, because we have to come to a major shift as well due to more and more electric vehicles in the system, but also due to more and more renewable energy in the system. We had in the first half year in Germany this year, I know it was a special year, but we had close to 60% renewable energy in the system. We need to bring that smart together and combine it. And V2G or V1G and V2G, you could also say vehicle grid integration as a headline, is a very reasonable and proper solution and a very cost efficient one. Next one you can skip. This is just about Mobility House. You can read for yourself. Why V2G? It was mentioned already, CO2 is a major topic of the future. We see that the just discussed values or price tags of V2G are continuously rediscussed and will be increased. Also the European Commission, they want to tighten their CO2 targets for 2030 already. And you see the automotive industry, especially the truck industry, is yelling already. So we will not get rid of that topic. We all know why, and it's necessary. But an even more important topic by today is we need to get all these electric vehicles connected to the grid. And there, Vincent mentioned already different applications. That behind the meter topic is key today, because otherwise you can't connect more than a couple of vehicles behind one metering point. I'll go into that in a minute. And the third part is we can improve the total economics of the system, because we can increase the share of renewables, and we can also reduce the cost of integrating renewables as well as electric vehicles, because we do not need to extend the grid as actually necessary if we make everything digital and connected bidirectional. Next, please. How do we see that development? And if you please click, you will see that we have the target in Germany to achieve 65% of renewable energy. We also have, and Klaas said it in the beginning, the objective by the automotive industry to achieve 10 million vehicles in Germany which are electric. If you put that together, and I'm 100 gigawatt hours higher than Xaver was, we have 500 gigawatt hours of stationary storage in the market. Currently, we have 40 gigawatt hours. If you see that from a global perspective, look, there are a couple of 100 megawatts now installed in Australia. California, they want to install 2.4 gigawatt of stationary storage. You see that already stationary batteries are entering the market for certain applications. And as Vincent said, the business cases are tight today, but they will increase more renewable energy will enter the system. And at the end, we achieve three things. First, by that, and these 500 gigawatts is an investment of roughly 50 billion euros. So, and they are absolutely unutilized because a car is sitting 23 hours a day and driving just 40 kilometers, despite the battery would have a capacity of 400 kilometers. So we all want to make use of that and use all that investment much more efficiently. And by using it bidirectional, we made the calculation that we can nearly double the amount of CO2 savings an electric vehicle does anyhow over the lifetime by integrating more renewable energy. And also we make money out of that. And I show you an example a little bit later. And if we have the right regulation, we would not even need subsidy for that, or hardly any, perhaps just in the beginning, as Xaver said, because the hardware is expensive. But as Vincent already mentioned, there is no blocking point. It will go down in price. It's just a matter of the beginning. How do we see the roadmap? If you click to the next slide, we are currently at the basis, which is everybody just needs to take care about charging. Can you go to the next slide, please? And after private and fleet operators took care about charging, they will need to take care about how do I minimize the cost? How do I get 3, 4, 5 cars integrated behind one metering point or in a multi-dwelling, in a condominium? As we all know, the grid connection is not made for that. And then we see the whole V2G, vehicle to home stuff appearing. We are just doing in pilots by today. How does, if you click to the next slide, the first step, the minimizing cost, the V1G, as mentioned before, look like? And I show you a real life example, and we have more than 200, I think 250 fleets now connected with our charge pilots, and whom we are controlling smart. These are this is a corporate parking place where 20 EVs are coming in the morning and between 6:30 and 10:30. If all those cars would just plug in with 11 kilowatt, you would have that 175 kilowatt peak in the very beginning. You would have 15K of grid 1,000 euros of initial grid connection to pay to the DSO, and you would have around 20,000 euros, 19,000 euros really demand charges. This you pay every year if you do not charge smart. If you look to the right side, and if you do that smart, and even as Xaver showed with an app and with a fleet schedule, so you would know when your employees come and leave, you could save 80% of that cost. So you would reduce the grid connection to 3,000 euros and the demand charges to 4,000 euros. So these are significant savings, first for the fleet operator or the industry player, but also for the DSO, because they do not need to extend the grid, which they can't do anyhow fast, because you need to dig up the road and put more copper into it. So we need more silicon and not more copper, and this we can do behind the meter already today, and that's an immediate business case by today. Then next shift would be kind of to V2G, vehicle to home. If you click one slide further ahead, and I don't want to go into any details, just 3 words to that. Please move forward. The vehicles work in the electricity grid. Vincent did that with NLX and Nuve, which they are also entering the market heavily on the V2G side and doing quite a good job, especially in the US. Showed it in Denmark. We did that in Germany together with colleagues of Axel Kiesling from the Amprion side and ENSO-E. That car is connected to the grid. It's an official power plant. It's registered in Germany with 7 kilowatts, the smallest power plant Germany has in the primary control mechanism. And that car earns around, if it would be continuously connected, 900 euros, as we also drive it during the day. So we earn around €5 currently with that vehicle, just with one product, just with FCR, frequency control reserve, which is the most complicated product in the energy market, because you have to react very fast. And if it's proven that an electric vehicle can do the most complicated product, all the other things we will be able to do in the future too with electric vehicles. We just need to have the regulatory framework. And another example, if you click ahead, and would be an island we did together with Renault with 20 unidirectional cars, so V1G, and 2 bidirectional cars. They are all connected to the grid, to a solar field, and also to a wind park. And they achieved, and I'm talking just about 22 electric vehicles, and there are around 1,000 vehicles on that island. These 22 electric vehicles achieved an increase of the renewable share of 2% on that island, so from 15 to 17. So this was the pilot to show that it works, to establish the control system. We are connected there to the kind of system of the island, which is a huge ABB system, because the whole island is powered by fossil fuel, actually diesel. And this, the grid operator there, they want to cut it off or just have it as an emergency backup. And it was proven that electric vehicles can do that job bidirectionally, but also to some extent unidirectionally. And now it will be rolled out subsequently further, so that we can increase the renewable share significantly. And as it was explained before already, I would like to ask you to click forward to the last slide, which is the very black one, just with 4 bullet points. There I summarized what is necessary that we realize these 2 CO2. Just click forward, please. This to achieve the CO2 reduction, and one back, please, and make revenue out of V2G. And as mentioned before, the revenue part is really tough. It's possible behind the meter, but it's not possible in front of the meter. So what do we need for that? And some things are already laid foundationally in the Green New Deal and in some countries locally translation. First, we need to have intelligent, ideally bidirectional charging station all over. If we can't control the charge point, we will not be able to digitalize our grid. So we recommend from Mobility House, our customers, whenever they connect something, just connect something smart. This is not a big effort. You just need to have a connection and OCPP 1.6 fully with all functionalities upwards, ideally 2.0, 0.1 actually when it comes out finally. Then we can control that charge point, and it's ready for the future. The sooner we get bidirectional charge points or vehicles, being it AC or DC, I leave it with the industry players, the better. Then we need to have targets for a scalable technical framework. So meaning communication. Smart meter gateway is not smart. It's another hardware piece, and it's German specific. We can scale and make a European market out of that. We need several standards to communicate. So we need something on a European level. And for sure, as Xaver was mentioning, it has to be safe. And we also need billing standards which are efficient. So the German Eichrecht, which is even known like kindergarten in English, and it's a catastrophe, is not an efficient and scalable standard. So there we need regulation for that. Then we need to have mobile storages as well as stationary storage. No taxes on mobile storages, similar to stationary ones. And whenever cars are integrated smart and charge smart or discharge smart, we need to have grid-friendly regulation so that we get money out of that. So the flexibility has to be honored by the players in the market, being it a DSO, being it an energy company, or being it a TSO. But I think Axel Kiesling will say something to that soon. So this, in a nutshell, we see the roadmap via unidirectional charging behind the meter towards bidirectional charging in front of the meter. But especially for the latter, we need some regulatory framework changes, and that's what Vincent and I and the whole CharIN team is working heavily for, to have that on a European and not a local country-wise level. Thank you very much for your attention, and open for questions now and later.
All right. Thank you, Markus. That was a really good presentation, and with the great interest followed your project on the Portuguese island of Madeira in Porto Santo, I think, with was it Nissan Leaf? No, Renault's. Was it
just
Renault's
AC.
or Nissan Leaf's?
Renault Zoe is AC, bidirectional AC.
All right, all right. Well, this leads over to the question we have from the audience. Which EVs today support bidirectional charging?
Actually, many, but most of the times we don't know it, because most of the vehicles can discharge in a workshop mode. So if you bring, I don't know it for the i3, but if you bring an ID3, for example, to a workshop, the workshop can discharge that car. So it's not so complicated. It's more a matter of the standard, as mentioned in the very beginning. But on a serious level, it's just the Nissan Leaf and the Mitsubishi, and it's the BYD, which I know that they can do bidirectional charging, as well as a couple of American school buses. I think it's especially the Bluebird ones.
Exactly. Yeah. I mean, especially now with the wildfires going on and the grid being under stress, you see they're like rolling blackouts basically by Pacific Gas and Electric, and this is where these American school buses with BGG come in very handy at the moment, and will come so in the future. Definitely, yeah. The Mitsubishi iMIF, actually, I've never seen them being deployed in any projects.
No, sorry. The iMIF can do it also. They are project. Enel did that, or Endesa in the very beginning in, I think it was a Malaga project. I meant the Outlander. I mixed it up. But the iMIF also should be able to do that, because it's also on the CHAdeMO standard.
The Outlander, right? Yeah. Okay. I mean, CHAdeMO-based Nissan Leaf is probably the one that is most used in those projects we see so far, at least in Europe. I guess this might change, given that Nissan said basically goodbye to CHAdeMO in Europe and North America. So interesting times ahead for CCS and ISO 15118. Yes. Well, there are some more questions, but I will leave it to the panel. And thank you, Markus, for now. I would then ask Axel Kiesling to present his presentation. All right, perfect. Mr. Kiesling, are you ready?
Oh, yeah.
Yes.
Good morning, everyone,
Perfect.
and welcome. Yeah, and also happy to have the invitation to be here and give a short presentation, because I think it's becoming more and more important that different industry sectors talk together, and sector coupling is becoming also more and more important. And here we have the opportunity that electricity sector and transport sector can come together and talk about what's going on, and what we expect in the future. And that also motivated me to do the presentation also from a content side, more broader, and also to explain what happens in the electricity sector, what we're expecting in the coming years, and also what does a change in the energy transition means for all of us. And yeah, so also, yeah, Xaver and Markus related to my presentation. So yeah, hope that I can meet your expectation here and also from the audience. And yeah, so let's start. And if you could, yeah, go to the next slide. Yeah, that's more for a physical meeting. But also if you cannot meet physically, I think that's also applicable for the different locations where you are. So safety is always important. And yeah, then let's come to the next slide. Yeah, so TenneT, the leading European TSO. So TSO stands for Transmission System Operator, meaning yeah, responsible for the extra high voltage and high voltage grid. We are active in the Netherlands and in part of Germany. In Germany, in the middle of Germany, from the north to the south. Yeah, here some key figures about the grids, end users, and the employees, so that you have a flavor what's TenneT about. And then you can yeah, go to the next slide. Yeah, so I mentioned transmission system operator. So what are the key tasks of a TSO? On the one hand, we have the transmission services. That's really meaning the planning, construction, and maintaining robust high extra and extra high voltage grid. That's one. And on the other hand, it was also related to the presentations before. We are also responsible for the system services, meaning maintaining the balance between electricity supply and demand at all times. So there we have frequency products for the grid. And on the other hand, also a key task is a market facilitation, that we have functioning, efficient, liquid, and stable electricity market. So that are the key tasks of TSO. And then you can switch to the next slide. Yeah. So, and a grid for renewables. And yeah, before I yeah, started my position for the flexibility and digital development, I also have an experience of more than 15 years in the renewables. And yeah, and that is really a fundamental change, the energy transition. So in the past, yeah, we had the big conventional power plants. And on the other hand, we have the demand of electricity. And yeah, the big power plants produced that electricity that was related to the demand. So you could steer this kind of power plants, and that you could do 8,760 hours per year. And you also had these big power plants near to the consumption of electricity. So let's say more or less a system that was easy to manage. And what happens now with the energy transition? So we have now a production, and the production is not related to the demand of electricity. It's more the production is really related to the weather, meaning if the sun is shining, the wind is blowing, then you have the production of electricity. You also have the production of electricity, for example, in Germany, the windmills in the northern part of Germany. And that also means you really choose your location for the renewable power plants where you have good weather conditions, but that is not closely related to the consumption areas. For example, you have the consumption in Germany more in the south, and the production with the wind onshore and offshore for sure in the north of part of Germany. So then you have to transport this electricity in the consumption centers. And for sure, because you have to balance then the consumption to the feed-in of electricity, and for these you need storage facilities. And for sure, you also have then much more power plants, because yeah, you have small power plants on the roof. So and that's more or less describing a fundamental change in the energy world. Next slide, please. Yeah, and that was also more or less, I think I saw similar slides in the presentations before. So, but more or less that's really yeah, related also to this slide here. So the renewable energy sources will increase. We have 43%, but we will have a growth to 2030, but also to 2050. So that means we are getting more fluctuating energy sources into the grid, and that also means we have to look for flexibility sources. So, and I, from my perspective, have always 3 dimensions of flexibility sources in mind. On the one hand, you have the existing power plants and the conventional power plants you can use for flexibility. Then on the other hand, you can have new technologies that you can build, like power to gas, power to heat. That's the second dimension. And what we are talking here today, that is for me the third dimension, and that is flexibility sources you have already in the system, but you have to unlock these flexibility sources, and that is, for example, to steer and to integrate into the grid electric cars, but that could also be home storage systems, or, for example, heat pumps. So, and for this type of flexibilities, and to unlock these flexibilities, you need digital solutions to integrate this in the market and the system. Yeah, next slide, please. Yeah, and that also describes then the innovation areas of TenneT. And for sure, on the one hand, we need the visibility, so we need the data if we are in a decentralized energy system, and we have to forecast. For example, we started years ago that we had to improve the forecasts for the renewables. So for the day ahead time frame, for example, but also for the intraday, what weather situation do we expect? What is the infeed of wind and PV, photovoltaic? But on the other hand, and that's getting becoming more and more important, is then also the consumption, especially if we have electric cars in the grid. What does it mean then for the consumption? What is the pattern of loading and charging electric vehicles? So visibility and forecast, this is a very important task for the electricity system on the consumption side, but also on the generation side. Then also, that was already mentioned in the presentations before, for sure the regulation and the legal framework is, let's say, designed for the more or less conventional energy system, and for sure there are also adaptations already seen in the legal framework and the regulation. But if we want to have the full capability of the smaller flexibility sources, then for sure I think it's an ongoing process for the adoption of the legal and regulatory framework, and that then relates to the market design also for the products. And what also is very important for the new energy system is that we unlock flexibility sources for storage. That is a cornerstone also for the energy transition. And for sure, we have to build new lines for the extra high voltage grid to transport the energy, for example, in Germany, then from the north to the south. Next slide, please. Yeah, and then what do we did for the vehicle to grid, or how did we start that? And we have seen that we have cars, and it's really to get to give a flavor what we are doing here. We said, yeah, we have cars that can bidirectional charging, meaning charging and discharging. And what I meant before, we have then also the generation of electricity in the north, and on the other hand, the consumption in the south. And yeah, we are still building lines to transport the capacity of this electricity from the north to the south. And in the meantime, yeah, we have congestion. That means that we cannot transport the energy from the north to the south, and that's then a congestion. And we have to manage these congestions via redispatch or congestion management. And for that, we also tried to use cars, how that could work. And we did that together with Markus and Mobility House in a pilot project, so that we said if we have a surplus of energy in the north, then we have to store it. And for this storage of electricity, we use cars. So that's very easy, because then you only have to say, okay, I have to charge now my car. It's more interesting than in the south, because that's the grid is imbalanced. Then you have to stop charging car, or you have to discharge the car. The grid is balanced. And for sure, if you have a vehicle to grid car, then you have more possibilities. So that meaning that it's more than only stopping the charging or slowing down the charging. Then you really can also discharge your car, and that has to be in the same time frame. And we tested it, because there you need really digital solutions, and you need also new algorithms that you really can steer that. And also that what's always important is comfort for the customer, that you don't lose comfort for the customer, that owner of the car can drive if he wants to drive. And so that was really a good pilot what we did here, to learn more about, on the one hand, the technical features of the cars, on the other hand also how we can come to algorithms that make that happen. And also that a customer has no lose of comfort. And for sure also to see what does it mean for the regulation, for example, that we need a motivation for these car owners to participate in the market. And also that's an important outcome of this congestion management or redispatch pilot, what we did with Mobility House and Nissan. Yeah, next slide, please. Yeah, so, and what also was mentioned before, so yeah, it's really sometimes repeating also from a content side. So if you have a lot of smaller flexibilities, then you have to combine these flexibility sources. And that means that, for example, you can combine windmills together with electric cars, or you can combine let's say home storage together with car batteries. And that means that you build with these many smaller flexibilities. And for sure that's then a market function of an aggregator to build algorithms to allocate different energy sources, that you really then build a virtual power plant that you can then participate in the ancillary service markets and offer your capacity, and then also earn money from the market of, for example, ancillary services. So that's what we also see in the last year is growing and growing, and many aggregators are stepping in these virtual power plants and building these. And I also assume, if, for example, the feed-in tariff in Germany for the renewables will be stopped after 20 years. We will see more and more decentralized flexibilities, and you also have to make use of that. And then, I think that will be grow and grow within the next years. Yeah, then the next slide, please. Yeah, and with these virtual power plants, we also worked together with aggregators, with two other pilot projects. On the one hand, in the Netherlands, we started a pilot project with Vanderbron, and there we used Teslas, or Vanderbron used Teslas for frequency product AFRR, and to deliver this product to the market. And steer the Teslas, stop charging then, and bring electricity to the grid, so that you then also stabilize the grid. That was one pilot we did in the Netherlands with blockchain, because we also have to orchestrate many devices then there, and I will come later to that, why blockchain. So it's not that we did blockchain because blockchain, everyone is doing a project with blockchain. It was more about that we really have many stakeholders in this new decentralized energy world that need access to data on the one hand, but on the other hand, we also need a data source we can trust, and blockchain you can trust, because it's you cannot change the data in it. So that was one project we did in the Netherlands with blockchain, and in Germany we did blockchain project together with Sonnen, and there we used the home storage, but on the other hand, for sure, you can also use electric cars, whatever. So it's really designed for smaller flexibilities, and to unlock these flexibilities. And with the blockchain technology, we made a good experience in these pilots, and that's then also was lessons learned and this experience that you can switch to the next slide, please. That we started a cooperation together with Terna and Swissgrid, based on this experience of the blockchain, that we really make it Europe, or try to make it European-wide or in different markets, to unlock these smaller flexibilities in a standardized way. Because what we also learned is from the industry, if you have local flexibility markets and you have different flexibility platforms, that is challenging to connect in different ways to these different platforms. And that was the reason why we said, okay, let's then have a standardized way how we can unlock this flexibility. And these three TSOs started to build this ecosystem called Equity, and to unlock these smaller flexibilities. Next slide, please. Yeah, and our mission is, and I think that's always important, and I mentioned that before, that we support the energy transition by unlocking these smaller flexibilities, because it's a cheap way to unlock these flexibilities, because that flexibility exists, it's only locked, we have to unlock it, and also that there's an additional value for the owner of the flexibility sources. And we see equity as a significant driver and enabler for the energy transition by unlocking these smaller flexibilities within the next years. Yeah, and next slide, please. Yeah, and that is how the crowd balancing, called Equity Crowd Balancing Platform, works. So we use a blockchain because we see, and what's also described here, that we have many stakeholders and many parties that are involved in unlocking these flexibilities. We have the OEMs, for example, that have the data of the cars. We have the owner of the cars, who also needs data and also has to be connected to this blockchain. And very important part is also for the aggregator, because if you want to offer electricity and volumes to the market, then you have to build algorithms that you can aggregate the cars. Because you can also combine the cars with what I mentioned before, with other energy sources like home storage, windmills, etc. So that means needs a kind of intelligence, and the aggregators have this market function to come to these algorithms, offer the bids to the market, and then the TSO can, if you participate in the market and you won the tender, then for sure you will be activated if needed from the TSO. And what's also important, the distribution system operators play an important role because they need at least the data, what's happening in the grid, but also for the coordination of the decentralized flexibility, and also if they have congestions in the distribution grid, that they also can make use of this flexibility. So that shows that this crowd balancing platform is really an ecosystem with many stakeholders, and you need, it's important to make these data available for all stakeholders. And that is why we decided to use the blockchain, because it's a cheap way to unlock flexibility. It's a secure way to store the data and to transport the data. And you can have operations at least close to real time. And that's the ecosystem that we want to build and to grow within the next years. Thank you very much for the presentation.
Thank you, Dr. Kiesling, for this great presentation as well. I do have one question for you. First of all, I wanted to address a comment I did before, given CharDemo and the Nissan Leafs. So the news is, which I wanted to address, that CharDemo said with their new Nissan Ariya, they want to equip them with a CCS interface in Europe and North America, but the old Nissan Leafs are still being produced and sold to Europe, as far as I know. Not sure when this will end. Just wanted to clarify, as there was a comment or a question regarding my comment. All right, so now the question for you. Using the blockchain solution, what was the data consumption of the individual charging stations, and how did this impact the business case?
Yeah, so that's also important for us. So we are, as a TSO, in the regulated domain. So we don't care about business cases. That's not our function. So we have seen in the blockchain picture that we have the aggregator. The aggregator is a market function, and it's up to the market functions, the aggregator, to calculate a business case, to offer a business case to the end consumer. And that's not up to us. That's not our role. So we only have, for example, if you want to take part in the ancillary service market, you have to pre-qualify, what also Markus mentioned before. And that's that has to the same rules for everyone. And then if you participate in the tender and you win the tender, then you get the money. And or the aggregator, and then it's up to the aggregator what kind of business cases he is applying for the customer. Mm-hmm. But what we realized is, but I think that's logical. If you have a vehicle to grid application and use case, you can do more with the car because you can charge and discharge. If you only have a unidirectional car, then you have to be connected. But if your car is charged, then you can do nothing anymore. So, but that's the difference to the bidirectional cars.
Mm-hmm. True. I mean, we all hope that bidirectional charging will become more and more day-to-day technology we can use, and not just something fancy and expensive. It's hard to say when this will become reality, within the next 5 years, 2 years, or longer. I don't know.
However, that does not lead to misunderstandings. So for sure, you can earn more money if you have a bidirectional car, but you should not forget that you also have other cost structure for bidirectional charging equipment. That's also clear. So I think that's then really what are the assumptions for the business cases.
Mm-hmm. Okay. All right. So now we have heard all 4 presentations. We do only have like 20, maybe 25 minutes left for the panel discussion. I already received a lot of questions, interesting questions. So let's head right into the panel discussion. I would ask every panelist to activate their camera and microphone for those who do not have a camera possibility right now. And I'd say jump right into it. Let's start with the first question. Which ancillary services do you consider most promising for EVs? Is it more primary control, like I think it's a matter of seconds getting to react, secondary control up to 50 minutes, if I'm not mistaken, or tertiary control? Anyone can jump in.
Marcus from Mobility House, based on our experience, and I think Vincent showed it also before, it's neither nor. It will be a combination of various flexible products. And currently what we see, and also Xaver had that in his slides, is the standard arbitrage business. So supporting the grid when there is cheap renewable energy in to charge and before they need to start pickup plants, so not renewable energy anymore, to discharge. This seems to be, due to the fast reaction time of batteries, the most promising business case.
Complementary answer, maybe. If we were so agreed with Marcus, it might not be those. I mean, either primary, secondary, or tertiary reserves might not be the main things to begin with. But if you were to choose between these, I think it's batteries. So they react fast. It's actually faster if it's V2G. You can discharge the battery. Then if it is V1G, you actually have to do, well, basically demand response and calculate baselines and all of this. So I would say V2G, anything, including primary. V1G, probably medium to slow response times for batteries would be fine. And the last thing to consider, whenever looking at those services, pilots may show a certain value in a certain context. Think about scale up and volumes and how much volume of flexibility of each type will actually be needed at what cost, at what price when things scale up. There was an interesting case in the UK a couple years ago, first auction for stationary batteries and possibly EVs for fast frequency response. Oversubscribed. Actually, the price was no good. So the people who subscribed for this didn't quite get the remuneration they thought they would.
And to add to that, I think a battery, so it's not about the battery, it's more about the technical equipment around the battery and the reaction time. And so it depends what you can deliver with your device, and it doesn't matter if it's a car or a home battery or whatever. I think it really is the process in general has to be seen, and then you have to fulfill the pre-qualification conditions, and then you can participate. And that's I think, Marcus, you are very experienced here within the last years, and that's really a commercial task of an aggregator.
All right, thank you. Next question. Given that there are energy losses when discharging a battery with V2G, and then again when charging it again, will the marginal cost
I don't know if it's me, but we can't hear you, Mark.
I also can't hear Mark anymore.
We can't hear you.
So perhaps to hop in, it was about marginal cost because of losses. So at the end, the losses are in the range we experience between 5 and 10%. Yes, this you have, and this you need to consider in the business case. You can hardly do anything there except you improve technology.
Are there technical difficulties? Do you hear me?
Yeah, now I can
hear you. Now we hear you again.
Yeah.
Okay, sorry. Something wrong with my earpods. Technology sometimes is really screwing me over. So I repeat the question. Given that there are energy losses when discharging a battery with V2G and then charging again, will the marginal costs of V1G not always be lower than V2G? So V1G always comes first in the merit order of flexibility, and hence shouldn't we focus more on V1G than V2G? In the end, pausing charging of an ongoing session has the same effect as delivering energy from the battery.
Yeah, interesting question. Well, it depends on not only the technology, but also the economic and regulatory environment around it. First, do you actually pay megawatts the same way that you pay watts? Basically, you pay negative. So do you remunerate demand response like you remunerate production? If you do, that's one thing. That's one advantage on V1G. But it's not the case everywhere, number one. Number two, there are needs of the grid that will probably be better fulfilled by V2G, by the ability to discharge. And on that, I will certainly Axel has a perspective on where capacity, actual production capacity from batteries would be needed to balance things out. So I would say from the technical need perspective, some of these needs might not be just fulfilled equally by demand management. And if the needs are different and they're specific, then there is a price to them. Right? So no, I don't think it would always be the case that V2G has a worse economic case than V1G. But for now, for sure, yes.
Any other opinions on that topic?
Yes, this is Christopher Trump.
Yeah, that's good.
Okay. What we have learned is that the value content of V1G has some certain limits due to the available charging time and, of course, the amount of energy that has to be charged. And if typically during one charging system only 10 kilowatt hours are necessary for daily driving, then you have some certain limitations also in terms of the value content, independently of which services you may want to do with V1G. In terms of V2G, you have a very good opportunity to mitigate these very close limitations from V1 to G, because you can expand charging time to the ultimate limits of being plugged in. And in terms of the state of charge level of the battery, you can still keep below 100%, which means you can at least be active as long as the customer has its vehicle plugged in. And this is a very interesting advantage of V2G versus V1G.
Just can confirm was Xaver said, and you have seen the Porto Santo Island. We just had 2 bidirectional cars there. We could achieve much more with more, because V1G cars are always filled pretty fast if they are connected. And also, as mentioned before, we BMW sees with the kind of improvement of self-consumption, you need to be able to fulfill that if you discharge the car at night. So you charge during the day with the sun and you discharge your car at night. So many of those use cases you have seen on the slides before are only feasible with bidirectionality.
And given that we need to make use and harness the availability of renewable energy as possible. And given the nature that they're intermittent, sun during the day, maybe wind at night. I mean, we need to make sure we don't shut off those windmills or like tilt the power of the solar panels in a certain way to not overload the grid, but use the cars to charge when this excess renewable energy is available, and then discharge it in the evening when there is maybe less renewable energy. And I hope this will always be a positive case on the merit order. Or at least.
What I also think is important, and we also we are active in the BMW project, for example, but also with us Nissan project we did. What's also important is, and I think that's you can do that, is that on the one hand you can really use the storage of the car and also for the grid, but on the other hand I think that's also important that you have the customer in your mind, that the customer does not have any kind of loss of comfort, because I think to make that happen in a scalable way, and if you have millions of cars and you want to use these cars, you need the acceptance of the customer. And that's not earning money, that's also that the customer really feels comfortable to drive with its car if he wants to drive. And that's a prerequisite to make that a success story with a vehicle to grid, I would say.
Hey. Great. Let's go on to our next question. Which hardware is most expensive? The one or more expensive? The one on the EV side or the one on the EVSE side for V2G? Who has some experience here? No comment so far?
This is also Xaver. From our learnings now, the main cost component is the bidirectional, and here you can consider two various concepts. The first one would be to have the bidirectional charger inside the vehicle, and you have already on it AC to inject into the grid. Or alternatively, you put the bidirectional charger into the EVSE infrastructure, which is from today's perspective a preferred solution from an OEM's perspective, because we are always interested to save weight, costs, and also space inside the vehicle. So currently now, and also in our BDL project, we are heading for the DC reverse power injection concept with the bidirectional charger on the wallbox side.
Mm-hmm. Okay.
The cost situation, it would be too complex to give a holistic answer today. But what you have to consider is where is it possible to implement the inverter at lowest cost. Here there are some pros, but there is a non-technical to have in mind as well. This is logistics. Please consider from country to country you have various differences in the grid codes and in the connection standards, especially feeding in power into the grid. In Europe, for instance, we have learned that there are 26 different standards you have to fulfill. And this would mean if you want to implement the inverter into the vehicle, you would create, even in Europe, 26 different variants. Handling challenge. For this purpose, the inverter on the DC side, on the wallbox, seems to be more interesting because especially PV inverter manufacturers have learned to handle this very interesting different situation from country to country. Thank you.
Isn't this also more of a software matter? I mean, these grid codes are basically can be encoded into a set of instructions for the inverter. So if the
covered is then using a protocol. We have some background noise here. Then using a protocol, you could communicate the necessary information, such as the target frequency, the cosmos phi, and so on. It's more complicated for AC than for DC, because DC externalized infrastructure. But would you not say we can, using ISO 15108-20, have a common solution that works across Europe?
If this was a question to me, it was harder to understand, so could you please repeat it?
Oh, okay. The grid codes are basically a set of instructions, right, that can be encoded into a communication protocol, such as 15118-20. That's what we are doing right now in the new version of 15118, trying to incorporate the baseline message necessary to let the car know this is the target frequency, this is the target voltage or the nominal voltage, this is the cosmos phi we expect from you, the kind of reactive power you need to fit in. Wouldn't that
this could be an option, and I'm quite interested to learn more about possible solutions. What we, I think, all together are missing right now is a holistic compare of these two different concepts and approaches, how to fit in by DC or DC from outside the vehicle. So I think CharIN would be a quite interesting community to create a group, for instance, in the working group Commission, to work together a very objective compare of these two approaches.
Just
sorry,
just one comment on this, and again, that's based on the question I understood. There are several standards that are, or norms that are relevant to this value chain of vehicle grid integration. And so CharIN is about one piece of it. I think whenever we look at how to expand or expand 15118, we should just be aware that there are other industry groups dealing with other pieces in the value chain according to, let's say, their own set of constraints. So I think perimeter or scope, particularly when you go to things that are related to grid and are being managed by energy companies or aggregators, etc. I think it's careful. We should be careful to look at the big picture of interoperability.
All right. Let's go over to another interesting question that just came in. Where is the benefit of user for bidirectional charging? Then currently, the way that the kilowatt price at the charging station is getting higher and higher, it seems to be, not a really good use case for the end user. So how would you incentivize the end user to provide a car for bidirectional charging at home?
Well, that's a simple one. So I can give it a try. A, economics. B, save the planet, green. And then C, impress your neighbor. But I would still start with economics and then almost equally save the planet.
But Vincent, you know the Germans buy a car to impress the neighbor, so you have to turn it around in Germany.
Right.
So you say it's probably a proper tariff that you have to sign up for, right? And if you provide your car or let your car provide VGT services, you get a cheaper tariff, because then a grid operator also has a benefit from it, and your mobility operator can buy energy cheaper from the grid, or how does it work?
I see it totally different. It will start with the example of American school buses we had before. So TCO-driven fleets, or the Rivians of this world, or Deutsche Post, or whomever. So wherever they can save money by operating their tool, which by coincidence is a vehicle, or make money out of it, they will do it. Before we have V2G at private customer in a mass market, This will take a while because then you have to have all these schemes and. But fleets are looking, and especially the American school bus market, very deeply into it already today.
Okay. I fully agree. I do think that V2G makes most sense for fleets where you have really a big aggregation of vehicles, especially when it comes to workplace charging or those parcel services like DPD or DHL or UPS. It's definitely going to be an interesting use case, and out of necessity, as we see in California, or actually also in Japan, where the original idea came up due to outages of due to earthquakes. Not sure how often we see earthquakes right now, but one of the major ideas how V2G came into existence, I think, was originating from that circumstance. Another question we have: could EV manufacturers gain CO2 credits if end users use an EV for V2G services?
It's already happening.
Okay.
It's already happening in the US. It's called the Low Carbon Fuel Standard, and it's very active in California.
All right. All right. Any other insights or comments on that? All right, next question. There are close to 50 million EVs in Germany. Once they are all electrified and can charge at around 10 kilowatts, this represents 500 gigawatts of flexible power. If only 5% of that power could be mobilized through V1G, that's still 25 gigawatt of flexibility at zero marginal costs. Isn't that more than enough flexibility? And if so, will V2G, which is more expensive due to the losses, ever get its turn? I guess.
Yes, that's just the right question. I think today you can imagine various answers because it depends on how many customers will decide in the next year their buying decision for a new car to an electric vehicle. And if yes, how many of them can run with intelligent charging or even with bidirectional? So what we will see will be a growing share of electric vehicles, and within that, a growing share with the capabilities of intelligent or bidirectional charging, which means that it's no digital step from 0 to 50 million electric vehicles. It's a more or less continuously growing pathway, which is now lying for us. And on the other side, the question is, what about the costs of bidirectional charging infrastructure? What can be cost estimations from the end customer's perspectives? So will it be profitable to make an additional investment for bidirectional charging equipment? And third aspect is how robust are the saving or the earning potentials, especially with grid services, because what we also see is, but in a more long term, that with growing amounts of electric vehicles which are entering the electricity market, you will see earlier or later some saturation effects, which will bring the costs or the revenues under pressure. And so it's a very interesting multidimensional calculation.
All right. All right. Unfortunately, we are running out of time. So I have one last question from my side. Do you see V2G more in AC chargers or in DC chargers in the near future, the next, say, 5 years?
Okay, then I try to start with my response on that and my statement. For long term, I think the race is open, whether AC or DC reverse charging will be successful. For the near term, we see that here the DC concept has significant advantages because it's far more easier to implement for an OEM to develop or to bring it into serious production compared to the AC concept. And even with respect to all the security and safety requirements coming up with injecting power into the grid, it's also far more easier to use the existing know-how from, for instance, PV manufacturers, from PV inverters, than to do the same job directly inside the vehicle.
I would like to add that from the perspective of CharIN and CCS, and that is one of the big assets, so that it's no necessity to decide, but let the market play on that field. I agree on Xaver on that, but so we did not restrict our charging system to only one technology, and that is a big advantage and gives us a lot of opportunities towards any other things which have been designed in Far East and concentrating only on DC. And so we see different opportunities. We will see that in cars, and I hopefully see that in every car the capability either with DC or AC. And let's continue on stabilize the ISO 15118-20, which incorporates both technologies, and we'll find applications and nice project for it to drive it further. And I recommend the guys in GB, or what is the name, Xiao something 3.x whatever. So that could make sense in Asia too, if that is going to market to broaden the perspective when moving from GBT and CHAdeMO to the new technology. So I would thank to everybody, have to hurry out. Thanks to moderators, speakers, panelists, the vivid auditorium. So we had 186 participants at the end, and seeing from the questions, so that is a success. If any recommendations from the auditor, from the participants for further formats and ideas and subjects to talk about, please let us know, and we will continue on this CharIN Tuesday format, and hopefully we see you again. I would say goodbye on behalf of CharIN.
Thank you. And thank you all for participating, and in particular for the panelists and their time for sharing all these valuable insights into V2G. I mean, it has become clear that there's already a lot of momentum in the industry with lots of projects going on, but we're still facing also a lot of challenges, be it on the regulatory side or on the cost side. However, we need to all work collaboratively to push the regulators to release the necessary policies so that we can make V2G happen on a big scale, which also helps to accelerate our path to 100% renewable energies.